Here's problem 37.1. A laser beam, wavelength 694 nanometers, is incident on two slits 0.1 millimeters apart. Approximately how far apart in meters will the bright interference fringes be on the screen 5 meters from the double slits? So our basic setup is we're going to have a screen a distance L away, and we'll have two slits which will be separated by a distance D. There will be light coming from these slits that will form an interference, constructive interference at some point, giving us a maxima at a distance y from the central point on the screen. And this will be at some angle theta. If we look at these two interfering paths of light, we find that from the separation distance between the slits, the path difference between these two paths will be equal to this distance right here, which, if this is the same angle theta here, then we'll have that d sine theta will be that distance. And if that's equal to an integral number of wavelengths, then we'll have constructive interference. This integer is called the order number, and it's 0, plus or minus 1, plus or minus 2, and so forth. So looking at the geometry of our triangle here, we would have that the tangent of theta is equal to the opposite side over the adjacent side, so that y is equal to L tangent theta. But it's really a small angles, very small angles, so you could say that y is actually equal to L sine theta using the small angle approximation. And taking our sine theta from this equation over here, we can substitute in there, and we have that y would be equal to L times the sine of theta, which we could write as m lambda over d. So y in general is going to equal, I want to write it this way, lambda L over d times m. Okay, so that would give us the point on the screen from our central maximum. But let's say we had two successive bright interference fringes. And so if we found our change between those two, our distance between those two fringes, that would be equal to lambda L over d times our change in m, change in our order number between those 2 points. Just like a differential equation, if we're taking the derivative of y with respect to m, then the m would be the only thing that's be changing as we change our y. And in this case, our delta m is actually going to be equal to 1 because we're just going from one integer to the next integer, either up or down. So our change in y is simply going to be equal to our wavelength times the length from the screen over the slit separation distance d. Okay, so in this case, our delta y is lambda L over d, and we have 694 nanometers, 694 times 10 to the minus 9 meters, times L, which is 5 meters, over d, which is 0.1 millimeters, which would be 10 to the minus 4 meters. And what is that going to give us? .0347. Everything is in meters, so that's going to be meters. That will be the separation distance between successive maxima on the screen, which is about 3.5 centimeters. That's well within visual limit, 3.5 centimeters. That's almost 2 inches, and so we would definitely see that on the screen. The nice thing about this equation is if we were to measure that kind of distance, and if we knew what our L was and our D, then we could reverse engineer this equation and figure out the wavelength of the light. So that's very useful.